We have done everything. Now start with Schrodinger equation. Okay, another postulate. Quantum mechanics. Schrodinger equation. Okay. Equation. Okay. First start with time dependent Schrodinger equation. Time dependent Schrodinger. The general equation is time dependent Schrodinger equation. Okay. Time dependent Schrodinger equation. IH cross del psi over del t. Del psi over del t means how is this wave function changing with time? Okay, we have a wave function, and now you put it in some condition, some Hamiltonian, somewhere. Okay, and you want to see how this wave function is changing. How will you see this wave function changing time? You will plug this, and you should know this Hamiltonian. Okay, is the action of Hamiltonian acting on this psi of x comma t is the action of this Hamiltonian. What is the Hamiltonian? H is p square upon 2m plus some potential v of x in one dimension. Everything is decided by this potential. Every solution of the problem will be decided by this potential. This potential in general can be a time dependent function. This potential, okay, let me not write it in 1D, let me write it in 3D, so that the generalization becomes clear. Okay, the generalization becomes clear. IH cross del by del t of psi of r comma t is the action of this Hamiltonian operator on psi of r comma t. Yeah, okay, where h is p, okay, vector square divided by 2m. P vector square means p dot p plus v of r comma t. Okay, and p square can be written different for spherical polar coordinate, different for spherical, different for Cartesian. In Cartesian coordinates, px square plus py square plus pz square plus qn, right? Is that okay? In spherical polar coordinates, is del square minus I cross square del square. Del square is general, in general it's just del square. Okay, so Hamilton, this equation becomes I cross del psi by del t r comma t is minus h cross square upon 2m del square psi of r comma t plus v r comma t psi of r comma t. This is the general, most general Schrodinger equation. The 3D Schrodinger equation. You can change it to 1D and 2D depending on del square, right? No, harmonic oscillator is not time dependent potential. Now, if you put a perturbation on this, then it will have time dependent potential. Switch on electric field, that is time dependent. The potential will change, right? Potential will be some plus minus EE of R comma T. Because what is your potential? Potential is nothing but E and E. Work that is just charge multiplied by potential, right? Is that okay? Then it will be time dependent. The time will be time dependent potential. Depends on it. Depends on what you are switching on. If it's switching on an electromagnetic field, then it's a time dependent potential. Yeah, if you part of a system, then the problem becomes very, very messy. It's not an easy problem to solve. We have some perturbative method to solve the problem, but that is also for weak perturbation. Okay, for strong perturbation, the answer becomes very, very complex. Okay, and we don't have that amount of measure, but for weak perturbation, we'll see. We have our okay. This is a very, very hard equation to solve because it's second order in space, first order in time. Okay, second order in space actually is already making it very, very complicated. Second order equation. Okay, you need two initial conditions in space to solve this. One initial condition in time. Second order difference in space. Okay, now this is time dependent Schrodinger equation because time is involved. Is that okay? What if time is not involved? The meaning of this is this will go away. No, not that. That's not the meaning of this. The meaning of time independent Schrodinger equation is an eigenvalue. Time. Yeah, you will give an eigenvalue. Stationary states. Time independent Schrodinger equation. It's an eigenvalue equation. Eigenvalue equation and eigenstates will be eigenstates of Hamiltonian. Okay, eigenvectors of Hamiltonian. Hamiltonian is just the sum of kinetic energy plus potential energy. Okay. Everybody familiar with eigenvalue and eigenvectors? That's the first point. I should ask also online. Okay. Online, anyone who is not familiar with eigenvalue and eigenvectors? Everybody familiar with eigenvalue and eigenvectors? Online? Okay. When this time dependent Schrodinger equation comes, I cross del psi by del t of r comma t equals to minus h cross square quantum del square psi of r comma t plus t of r comma t psi of r comma t, and you have to remove this time dependency of the potential. Whenever you have an eigenvalue equation, potential can't be dependent on time. Potential has to be space dependent. Otherwise, if the potential is time dependent, then the potential is changing from time to time. Then you can't have an eigenvalue equation. Eigenvalue equation is only possible when the potential is time independent. This original potential should be time independent. Then you are adding a perturbation, that is a different thing. You can't start with the time independent potential, time dependent potential for solving this. Equals to E psi of r comma t.
We are adding perturbation, that means we are considering weak perturbation.
Yeah, weak perturbation. And we'll see what this weak perturbation is. Okay. But in general, potential is not a function of time when you're solving. Okay. So E will be the eigenvalue of the Hamiltonian. And we'll see that the time is called as time independent because the time dependence of these states is just a phase factor. And we'll see what this phase factor is. Perturbation, we'll see what happens in perturbation. But before the first, we have started without perturbation. Is that okay? This is the time independent Schrodinger equation. This one. Time independent. Any doubt?
Time dependent Schrodinger equation is a different.
No, this is also a differential equation. But you'll get all you get is an eigenvalue of it. Okay. In time independent Schrodinger equation, you won't get an eigenvalue. Is that okay? You can start with any state. And that state should not be the eigenvalue of Hamiltonian. In time independent Schrodinger equation, you're guaranteed to get an eigenvalue of the Hamiltonian. With an eigenvalue and an eigenvector of Hamiltonian. That's the specificity of time independent Schrodinger equation. You're guaranteed to get an eigenvalue. Guaranteed to get an eigenvector. Okay? Yeah, energy eigen. You can get energy eigenstates by solving this equation, right? This is called as eigenstates of the Hamiltonian. Yeah, you can get measurable values. To start from here, h cross square upon 2m del square psi of r comma t plus v of r psi of r comma t equals to E psi of r comma t. Okay. So now the psi is a function of r and t. I can switch this. I can write some function of r multiplied by some function of t because it's a time independent. Time r and t. Some function of a of r, some function b of t. Any doubt? So del square. Some function of r, some function of t. Del square. Okay, this time dependent term will come out. Won't be differentiated by the space, right? These are space variables. Del square. Del 2 upon del x2, del 2 upon del y2, del 2 upon del z. And IH cross del psi upon del t, r and t will be equals to IH cross A of r, IH cross A of r del b upon del t. Find out. The psi is some function of r, some function of t. A will come out. A won't get differentiated because this is a function of space. Can't get partial differentiated by time. These are partial derivatives. Okay? Del b by del t.
Second step you did del square of that equation.
Del square is nothing. In Cartesian, you have del 2 upon del x2, plus del 2 upon del y2, plus del 2 upon del z2.
That is clear. Next step, you substituted.
No, I have touched this part is also here, right? Time dependence is also here. So H cross del psi by del t is H cross A of R del B by del t. Only this part will get differentiated with time. This part can't get differentiated with time. It's the space part. Call this equation number 1. Call this equation number 2. Okay. And now you have to compare. You can compare this with this first. This with this. Because this is equal to this and this is equal to this, right? Compare this with this. This is done. Up here done. Right? We have IH cross del psi upon del t R and t equals to E psi of R and t. Okay. We have IH cross del psi del by del t. What is the value of this from equation 2? From equation 2.
IH cross A of R del B by del T.
IH cross A of R del B by del t equals to E A of R B of t, right? A of R cancels out from both sides. Del B upon B equals to minus I by H cross E del T. Integrate. Del B upon B. What is this? ln B. And what is this? It's just IE by H cross into T, right?
Because he's
Huh? Plus.
Yeah, he is constant.
Some ln, some constant, right? B naught. Okay. Write B naught, right? You want to write A, you can also write it A, but we have already taken A. So don't write this. So the final solution will be B equals to B naught e to the power minus I e t over H. Okay, this is basic elementary mathematics. Take here B naught, then ln A minus ln B is ln A upon B, right? And in order to remove the logarithm, you have to take the exponential, both sides, right? That's the anti-logarithmic function. So B equals to B naught e to the power minus I e. So you're seeing this? This is the time dependence of your wave function. This is a time dependence. B of t is some B naught e to the power minus e t upon H cross. Time dependence. I found out the time dependence.
B naught is not that.
B naught is not time dependent. The time dependence is sitting here. E to the power minus I e t. B naught is just a constant. You started from somewhere, right?
It's
Phase factor. We call it phase factor. This is called as phase factor. And it's irrelevant for us. Because if you take B star of t, you'll have a B naught star e to the power plus I e t over H cross, and B star of t, B of t will be B naught times B naught star, that will be mod B naught square. So whatever the time is, we don't care. We'll always get a B naught square. So we started from somewhere, the time dependency will not change. If it's an eigenstate of the Hamiltonian. If it's an eigenstate of the Hamiltonian, that's the important part. If it's an eigenstate of Hamiltonian, the time dependency is just a phase factor. The probability of finding the particle with time will not change. That's the meaning of this. So if a particle is in an eigenstate of Hamiltonian, the probability of finding the particle at any interval of time, t equals to 10 seconds, 15 seconds, 20 seconds, will not change with time.
provided it is the item.
So provided it's an eigenstate of Hamiltonian, because we started from there. So that's why it's called a time independent Schrodinger equation, because the eigenstate you get are independent of time. The probability of finding them is independent of time. Okay. So if a particle is an eigenstate of the Hamiltonian, one eigenstate of the Hamiltonian, the probability of finding it will not be changing with time. But we'll see the particle is never in the eigenstate of Hamiltonian. It's in a linear combination of eigenstates. Any general state will be a linear combination of all possible states, and then we have a problem. Then we start having problems. Then we start having cross terms. E1 minus E2, E2 minus E3, E3 minus E4. And then those terms don't cancel out. And then we have phenomena of beats, oscillations, right? Crazy phenomena start happening. It does not a Fourier series. We'll see what happens. Okay. This is okay. What about the space part? Space part is this, right? Minus h cross square upon 2m del square psi of r comma t plus v of r psi of r comma t equals to e psi of r comma t. Right out? Minus h cross square upon 2m del square, I was writing as b of t a del square a of r comma t plus v of r psi of r comma t is a of r b of t equals to e a of r b of t. Right out? Okay. Now divide by psi both sides. Divide by psi of divide by a of r b of t both sides. Okay, if you divide this by a of r b of t, b of t, b of t cancel out, you get h cross square upon 2m del square a of r comma t divided by a of r plus v of r equals to e of r. Sorry, e. And you have to solve this equation. Any doubt? You can't do for more than this. Okay, you have to solve this equation. Okay, we don't care about. Only thing we care about here is this part, time dependent part, which is gone. Space dependent part is just this a of r. Okay, and we have to solve this equation to calculate a of r. Okay, we have to solve this equation then. Solve this equation, and we'll see how to solve this equation when we do particle in the box, harmonic oscillator, and all. All we do is solve this equation, right? Solve this equation to get a of r. You can't go further than this because you need potential for solving this equation for a of r. But for that we need potential, right?
Each system has their own potential.
Each system has their own potential, own boundary condition, and we need this potential. Solve this. This is just for the sake of explanation that what happens. Right out. So in general, my solution is like this. Psi of r comma t will look like a of r and a b of t, right? A of r I can solve until unless I have potential, but b of t I have decided. This is b naught e to the power minus I e t for h cross. Okay, I'm writing my a of r equals to some phi of r. Okay, just a change of variables, nothing else. A b naught as some a. Okay, a constant. Psi of r t. Just don't get confused here. Okay, this b of r I'm replacing. A of r I'm writing as phi of r.
Very good.
B of r. Okay, if you get confused, then you write b of r c. Okay, a constant. C equals to constant. Okay, psi of r t equals to c phi of r e to the power minus I e t. So anytime you will have a time independent Schrodinger equation, this is the kind of solution you will get. All you have to do is this phi of r, find this phi of r, and everything will be taken care of. Everything will be taken care of in the solution. You already know the time dependence. It's just a phase factor. All you have to do is find this phi of r. And that's the whole job in whole quantum mechanics is to find this phi of r. For every problem, there's a different phi of r, and we'll find this phi of r.
Special part.
Huh?
Basically, special part.
The special part. What is special?